First, some updates. Yesterday, I posted another set of exercise questions for Module 1, Part C and D. So we have two sets of questions for Module 1. You can see the first set, 18 questions. Second, 24. Total 42 questions. And I also post the solution to AB part. But after I post the solution, one student pointed out a mistake. Not this class, online class. One student, question number 2, I did something wrong, so I corrected. So the current version should be correct. In the noon question,
Sorry, I'll wait till you're done. I'm sorry.
Right. So make sure you get the newest version. The problem is, I didn't go from the square size. Square size and the number of squares, because two different things. I use the square size directly. I should use the number of squares to do the calculation. That problem. So then I make that switch. So then I change the answer. Other than that, if you find other errors, so just let me know. So I may have some errors. And this weekend, I will post the answers to CD part this weekend. But this weekend, I will also post the quiz number 1. Okay? This weekend. Then we need to build up some more homework questions. So right now, so every time you get some homework questions in the exercise sets. So after probably next week, so we collect enough many so I can give you homework assignment. All right. So today we start Module 2, Analysis of Algorithm Efficiencies and a Brute Force Method. Part A, Problem Solving from Experience and Elimination Method. From Part D, we already apply elimination method a few times. So at this point, you should have some, good understanding on elimination method. In the new question set for C and D, I give you a few questions. You need to apply elimination method. A few questions. Elimination method. So it's simple, but you need to get used to the thinking, this kind of thinking way. It's not hard, but you need to make your adaptation to this elimination special thinking way. All right, 8.1, selection sort. So this is our first sort in this class. So we will have several. In this whole class, 5 or 6 sorts. This is the first one. Our question problem number 4, sort an array. The problem, very simple. Given an array with indices from 0 through n minus 1, how to sort it in ascending order. The problem is so short. Very easy to understand. The problem type, sort type. All right. Now let's do some analysis. Based on the title, when we sort, this particular question, at this time, we do not have a lot of background, right? We do not have much background in algorithms. So we only use our limited experience, background in algorithms to solve this problem. Okay? Let's try to find a solution. Yeah. There are many different solutions, but at this point, our knowledge is very limited. So our experience, we only have Module 1 experience. Right? That's the experience we can rely on, Module 1 experience. So here, we need to consider how do we apply our Module 1 experience to solve this problem. Okay? Yeah, that simple question. Yeah. All right. Find a solution from our experience. Yeah. All right. So how, in problem solving, it's the first thing you need to do, you try to understand the problem. How you understand, we try to explore certain properties in the given problem. Given this problem array, we want to sort it. Can we discover some special properties? If you can, then you can find some special algorithms based on your properties. Because there are so many different ways to discover different properties. Then you have many different algorithms to solve the same problem. Here, we want to find a simple solution. Our first solution for this sort problem. Yeah. All right. Yeah. So based on this guideline, so let's do this time do backward thinking. This is another commonly used problem solving thinking method, backward thinking for problem solving. Yeah. We start from the end result. Yeah. And do backward thinking. Okay? We assume that an array has already been sorted. Yeah. Yeah. So we want to assume if an array is already sorted, what special property we can observe here. Yeah. All right. If the array is sorted, what property we can discover? Okay? Yeah? Yeah. Yeah. Assumption, we assume distinct elements for convenience. Yeah. In the real world, when you sort an array, you cannot assume all elements are distinct. That's not good. Yeah, because the given data, even if it contains several duplicate elements, you still need to do the sorting, right? So in the real world, we cannot make this assumption. Yeah. But in our problem solving at the beginning, we can consider some relatively simpler case. Here, this distinct element, this case, simpler for us. So let's work on a simpler version. After we find a solution, then we remove this assumption. How about that? After we can find a solution, we just make small adjustment by removing this assumption. We just do a little more work. Actually, not too much work. Very little more. Okay? You can, remove this assumption. But early discussion, yeah, so we want to make our discussion as easy as possible. So we make this assumption. Distinct elements. All right. Then, regarding our experience in Module 1, yeah, here, so, just a few questions. Our question, problem 1, problem 2, problem 3. Only 3 problems, right? Yeah? Yeah. most closely related question, that's probably the minimum problem, closely related, okay, yeah, to this sort problem. So we want to see if we can use the result from finding the minimum, that problem, to help us solve this one. Okay, yeah. Yeah. Using our old experience. Yeah. All right. Yeah. Observation. Now we need to do backward thinking. Okay, this backward thinking is we consider the array already sorted, yeah, in ascending order. Now you observe this whole array. Can you discover some special property? Already sorted. Yeah. The property you should connect to our old experience, the minimum problem experience. Can you make some, connection? Yeah. So the property connect to our old one can be used to find a solution. That's what we want to do here. Okay? Yeah? Minimum, can you see the minimum? Right? The minimum. What is the minimum? Yeah. A0, right? Minimum. Yeah. All right. You apply the minimum problem solution on the given array, you can find the minimum, right? That minimum becomes the A0 here. How about that? Yeah? Apply the minimum problem solution, you find the minimum. Yeah? So, that minimum equals this A0. How about that? Okay? All right. So you can find A0 quickly, right? Yeah. After that, A0 is gone. How about A1? How do you find A1? Yeah, the minimum of the remaining elements, right? Another round, minimum solution. Then A1 is there, remove it. A2, how about that? Yeah. Every round, you find a new element, we call it new element in place. Then A0 is in place, right? Yeah. Then A1 in place. Then A2 in place, and so on. At the end, you get all elements in place. How about that? That's the idea. Simple, right? It is built, this solution is built on top of that minimum problem. See how simple it is? Okay? It may not be very efficient. Yeah, that's another question. It may not be very efficient. This is our first solution for solve problem. Okay? All right? Yeah. Now, based on that understanding, so let's complete. Yeah. A0 equals the minimum 0. The first time you apply the minimum solution problem. All right? So after that, we use this concept, in-place concept. So if an element is in its final location when the array is sorted, we call it in place. Yeah, yeah. Yeah, because when the array is sorted, each element has its right position in the ascending order, right? Yeah? Each element in the ascending order, it has its right position. That position, if the array element is at its right position, we call it in place. Okay? Yeah. If all the elements are in place, then it must be sorted. Yeah? So our goal, we want to make all elements in place. Then the whole array is sorted. Yeah. Just the terminology we use, in our discussion. Yeah. All right. the element is placed at the position when the array is sorted. Yeah. In place. Yeah. We use this concept. Then, elimination method, because if an array is already in place, we just remove it, right? Because we have no worry on it. Yeah, it's done. It's done. Let's simplify the problem. Remove it. Elimination method. Then another element in place, remove it, and so on. Okay? Yeah. That way we apply the elimination method. Yeah. All right. So then A1 equals min 1. Yeah. Another round, minimum solution application, and so on. Okay? Yeah. In each round, we place one element in place. Yeah. Think about how many rounds do you need to do before you put all elements in place? How many rounds? N minus 1. Yeah, not n. Because the last round you have only one element, it must be, yeah, only last position available. You do nothing, okay? So we do n minus 1 application of the minimum solution. Not n, n minus 1. Okay, yeah. All right. It also tells you if you place n minus 1 elements in place, then the last one you don't need to do anything, right? It's automatically in place. The last one is automatically in place. If you can put the n minus 1 elements in place, then it's done. Yeah. Only one left. Do nothing. Yeah. All right. How to make all elements in place? Yeah. So here. Final destination. So these n locations, that's the final destination locations. Okay? The first round, min 0 in place. Second round, min 1 in place. And so on. Okay? The last one automatically in place. Do nothing. Yeah. Now we need to calculate the number of comparisons. Okay. All right. The conclusion here. Yeah. When all the elements in the array are in place, the whole array is sorted. Simple. Yeah. Efficiency analysis. Yeah. So let's look at the efficiency. How many comparisons do we need? Yeah. Let us count the number of comparisons. In the first round, finding the minimum, we know the number of comparisons, finding the minimum, right? Yeah. The first round, n minus 1. Second round, n minus 2, going backward. Okay? Yeah. Then the last round, 1 comparison. Last 2 left, 1 comparison. Okay? Adding up, so you get this many comparisons. Okay? This many comparisons. Yeah. That's the total number of comparisons you need to sort the whole array using this algorithm. This algorithm, we give it a name, we call it selection sort. Yeah. Why selection sort? Why selection sort? Because the main step, each round, we apply that minimum solution problem. That's the selection problem. Yeah? Finding the minimum, it's a special selection problem. So we just apply one special selection problem, its solution here, so we called selection sort, the name. Okay? Yeah. Then, what's the best case? What is the worst case? What is the average case for this algorithm? Can you see that? Best case first. This way. What's the best you can do? Imagine some special input to give you the best, the smallest number of comparisons. That's the best. What's that number? Zero, you do nothing, you can sort it. Oh, even if you already sort it, how do you know it's sorted? Right? You need to do the work.
Sorry, I was just saying best case it might be arrays empty.
No, we assume array n elements. You cannot reduce that number. Okay? Yeah. The given array contains n elements. You cannot change that. That's the best case. For the given data, you can assume it's sorted. That's fine. Yeah, that's fine. If an array is sorted, how many comparisons do you need?
Still n minus 1, so still got to run through.
Correct. Correct. Still the same number. Because when you apply that, finding the minimum, that solution, even, you know, because you do not know, right? You have to, each round, you have to go through from beginning to the end. All the possible elements, all those elements that are not in place, you need to go through all of them, right? Yeah. Even if it's sorted, but you don't know, right? When you go through your data, how do you know it's sorted? The computer does not know. The computer cannot see the data. Okay? Even you store the data in memory, but computer is blind. It does not know your data is ordered. Okay? It has to do the work, same amount of work. Okay? So the best case. How about the worst case? Same. Same. How about the average case? Same. Because there is only one case. Okay? So here, whatever you do, only one case. If you have one case, the best case is this one, the worst case is this one, average is also this one. Okay? Same number. Yeah? Okay? Yeah? All right. That elimination method, here we summarize a little bit on this elimination method. The goal, reduce the problem size. Remember last time I mentioned one statement. I said, in general, or usually, the smaller the problem size, the easier the problem. But we put a general, or usually, that's not 100%. So that's most of the time we have this property, but there are some exceptions. Okay, I point out exception. Okay, prime factorization, that's the exception. Okay, yeah. So with that in your mind, in general, most of the time, 90-something%, it's correct. So we can apply it, right? Yeah. Exception, when we encountered exception cases, we just do some modification. Yeah. We change our way when we see exceptional cases. Yeah. Yeah. Here, we use the general case. Yeah. The smaller the problem size, the easier the problem. Yeah. But you need to know exceptional cases. Yeah. When some elements do not change the outcome, they can be eliminated from consideration. Yeah. Some of the elements, you already know the destination is there, it's inside, outside, whatever, it's there. You can take them away, so you do not need to consider those elements anymore, so you reduce the problem size. Okay? So that's the typical elimination method. Yeah. All right. Later, Although it looks so simple, right? It looks so natural based on our daily life experience. Everyone knows this, right? Everyone, based on your own experience. Everyone knows. But sometimes you may not be aware of it. Later, we will have such questions. So you can look at our second question set for Module 1, Part C and D, that one. There are a few questions. You are not aware of it. When you work on it, you try many different ways, but you do not know how to apply this elimination method. Okay, that's not easy. It's not obvious. It's not that obvious. Okay, later you will see. When I talk about the solutions, so you will see. It's not that obvious. Okay, you need to make a lot of effort to see that property. All right. 8.2, impact of organized data. So here, this topic. If the data is organized, what the benefit you can enjoy? Okay? What's the benefit you can enjoy if the data is organized? Because if you want to organize the data, it's not free. It's not free. You need to pay something, pay some effort, pay your time, pay your money to get the data ordered, organized. It's not free. You need to do a lot of work. The question is, if the benefit is worth the amount of work you invest. That's the question. Okay? If worth it or not. Sometimes it's worth it, sometimes it does not worth it. Okay? Here, I'll give you a simple question. So you can see if it's worth it or not. Let's look at our question, number 5. It's called element uniqueness problem. Given array, still array, general array, can you detect if each element inside this array is unique or not? So we call it element uniqueness. If there are duplicate elements, okay? If unique, distinct, that's our assumption in the previous sorting question. Distinct, unique. Here, but we need to do detection. If any given array, the elements inside unique or not. We need to use the minimum number of comparisons to do it. Okay? Think about that. Given an array, how to check if all the elements are distinct. And we want to use most efficient algorithm to solve. There are several different algorithms, but we want to use the most efficient one. Okay? So let's try a few, at least 2 different ways. Then we can compare which one is better. All right? Okay. Method 1, brute force method. Brute force, just do your comparisons immediately without doing anything for preparation. Do nothing in the preparation stage. Just do the comparisons immediately and see how many comparisons you need to do nothing to organize the data, brute force. Okay? So this step, preparation step, no cost, you save. Okay? There, but your data is not organized. So you need to do more work on that random data, right? The random data. Okay, yeah. So here, yeah, because the value is not that important. Yeah, just all the numbers are different. The value is not really important. So here I use the simple values here. Okay, all right. Because we only want to compare the same or different. All right, yeah. So here, now, the first round, we want to see if the first element appears anywhere in the remaining elements, right? If this 0 appears in other places, then we know if it appears somewhere else, it's not unique. So we're done. Yeah. Yeah. The function returns the value true, false. True, unique. False, not unique. Yeah. So we stop. False, not unique. Yeah. But that's for the first element, 0. Okay? Yeah. You need n minus 1 comparisons. Okay? Yeah. After that, then you look at 1. Does 1 appear somewhere later, right? Other places? So you need n minus 2 comparisons to see, worst case n minus 2, right? Probably the next one is 1, you stop, right? Yeah. So the worst case, you have to go through all of them, all the remaining elements to do the comparison. So n minus 2, the worst case. 2, next one, and so on, right? Yeah. So like that. This one, only do 1 comparison. See, same or not. So for the worst case, you add up all these comparison numbers. That's the worst case. Okay, yeah. The best case, what's the best case? 1, yeah. So 0, 0. 2 adjacent, 2 consecutive zeros, we are done. That's the best case, right? Yeah. So the best case, 1 comparison. The worst case, yeah, all these numbers add up. Okay? Yeah. Yeah. Even that, same or not, you need a 1 comparison. Okay? So the worst case, you need this many, 1/2 times n minus 1. Yeah. All right. Average case, yeah. Average case, yeah. Yeah. You can try, right? Yeah. Here, average case, yeah. Not too hard, you can try. Yeah. Average case. Yeah. All right. Yeah. As a simple practice. Yeah. Yeah. All right. Yeah. Yeah. So then, this is our first method. Second one, we are willing to pay for some cost to organize data. The second one. Yeah. Yeah. So we want to see if we can do better than the first one. Yeah. First one, we do nothing in the preparation. So we feel, we just put all our work on the comparisons. Don't waste our work on preparation step. Yeah. But now we want to see if we do some investment. Yeah. So this data organization becomes something useful, so we treat this part of the work as the investment. Because we can get a rewarding. Yeah. We can get a reward from this step. Yeah. Investment in data structure. Yeah. We sort the array first with certain cost. At the beginning, before we do the checking, let's sort the array first. How about that? Okay? Yeah. But when we do the sorting, definitely we cannot use our previous selection sort because that's a better one. Later, we will find many much better sorting algorithms. Here we just use, some later result, some better sorting algorithm we will learn later. Here we just get one. There are several sorting algorithms that can give us n log n number of comparisons. N log n, not n squared. Yeah. Our previous one, we get 1/2 n squared, but the previous one, that's 1/2 n squared. Yeah. But here, this log, we know, comparing with n, much smaller than n. Log, here log, you can treat as log base 2, much smaller. Why? Even we use log base 2, you can see if we put 1024 equals 10, right? See? Much smaller, right? Yeah. N equals, here. N equals 1024. After you take log base 2, it becomes 10. Is it much smaller? Right? Yeah. So that gives you the idea, sense. Yeah. Give you idea, n log n much smaller than n squared. Okay? Even 1/2 of n squared, still much larger than this n log n. Yeah. Yeah. Later, we have several algorithms. We can get this n log n efficiency. Yeah. So here we just borrow those one of such sorting algorithms. So we do this many comparisons to sort the whole array. Okay, all right. That's the preparation step. That's our investment step. We pay this much cost. Before we do the checking work, we pay this much cost. All right? Next, we want to see the benefit. If this investment is worth it or not, we want to see. Okay? How to check if any element is repeated in an ordered array. This time, we check in an ordered array. The previous time, we check element repeated in an unordered array, right? Can you see the main difference? How much work you can save in an ordered array versus unordered array. Okay? So you can see something. Yeah. Here, let's assume we have an ordered array. This time, in order to find two elements are the same in this ordered array, can you see some simple property? Yes. Two adjacent elements must be the same. Is that? If there are two elements the same, you can find two adjacent elements that must be the same, right? Yeah, two adjacent. Yeah. So when you do comparison, you can use that property. You only need to compare two adjacent elements, right? Always compare two adjacent elements. You do not need to skip, okay? Compare two elements that are not adjacent. You don't need to do that. Only compare two adjacent elements. Can you reduce your comparison numbers? Only two adjacent. See? Yeah. So we only need to compare two adjacent elements. Yeah. Here, if we write a pseudocode, then you write one for loop. Every time compare two adjacent. One scan, you're done. Right? How many comparisons do you need? Can you count it? N minus 1. Yeah. N minus 1. Yeah. the total n minus 1. The previous one, 1/2 times n minus 1, right? Yeah. Can you see this time much better than that 1/2 times n minus 1, right? Much better than that. Okay? Yeah. Although you invest some time, some comparisons in the preparation step, but still much less than this number, right? Yeah. So the investment worth it, right? Yeah, the investment. Yeah. You pay quite a bit, but the investment worth it. Okay? Because what do you need to do? C1 plus C2. Okay? The first part n log n plus the second part n minus 1. And you can see it should be much less than 1/2 times n minus 1. See? Yeah? All right. Yeah. Here. Yeah. So let's do summary a little bit. Yeah. Before we move to the next topic, let's do the summary a little bit. Yeah. So the summary, yeah. Think about. Yeah. Sometimes, yeah, we can only, it depends on the problem. Sometimes if we invest on data preparation, so the data preparation part, typically we organize our data. We use some special data structure to organize our data. Yeah. Yeah. Many times we can benefit from the pay we put there. Yeah. We have to pay, yeah, because that part not free, and that part you need to pay some cost. Yeah. All right. But to justify that investment, you need to see if you can improve your overall performance. Yeah. In this particular question, we can improve our overall performance. Okay? Yeah? Yeah. 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 So here, I didn't really do the math to compare which one is better. Yeah. In the next part, I will use calculate. I will use calculus method to compare. You know, this one is better than the first one. Yeah. I will do the math to do the comparison. Okay? Yeah? Yeah. All right. Yeah. So here. So yeah. So that's something we learned, yeah, from this example. Yeah. Another thing, I want to make some comments. Yeah. This question, it's a pretty simple. Yeah. Yeah. But it came from one of the interview questions. Yeah. Interview questions. Yeah. Yeah. Some companies are, you know, some usually top tier companies, when they look for programmers, they give algorithm questions to the candidates to work. You know, some questions very challenging, some easier. You know, different levels of algorithm questions. This one is one of the interview questions. Yeah. We can treat it as an easier one. Okay, this is a, you know, the level, because usually, you know, people put the difficulty level, you know, 1, 2, 3, 4, 5. Okay, yeah. So this is at a lower level. Yeah. Interview questions. Yeah. So you need to think about, yeah, if you happen to, you know, received a question like this, you know, how do you answer, right? So definitely you want to use the fastest algorithm. Yeah. The second one better than the first one. If you use the first one, you have no chance. Okay? Yeah. If you use the second one, you may have 50% chance. Yeah, not 100%. Yeah, because this second one is still not the best one. Yeah. There is another one that's better than this one. Yeah. So the third one, better than this, it needs to use another data structure, so that data structure is more advanced than we are using here. Here we use array in ascending order. That's our data structure, right? Array in ascending order. That's simple data structure. Yeah. Then here I like to talk about the third method. In this third method, it uses a special data structure called a hash table. Hash table. Hash table data structure. Yeah. Some of you may heard of that. Okay, may have heard of that. Yeah. Yeah. Hash table here. In our module 5, the second part B of module 5, we will learn basics of hash table data structure. Yeah. Here I just describe in a simple way this hash table. Okay? Yeah. Yeah. If we use a hash table to store the elements in this array, then we can get very fast algorithm, the third one. Third one, we use hashing, the technique we are using here, we call the hashing. Yeah. Hashing typically used for fast search. So that's what we are doing here. We're doing here fast search. Okay? All right. Yeah. So here, let me describe the idea. Yeah. At this point, probably still a little earlier, yeah, because if you do not have the background on the hash table data structure, so you may not get good understanding. Yeah. When we get to module 5, after that, then you can understand much better. Yeah. Here, I just give you some initial understanding. Yeah. All right. We know hash table, basically, it is a simple table with slots, okay? Yeah. A table with certain number of slots. Yeah. So here, let's say m slots. This m usually greater than the n, number of elements. So we have some room, okay, to manipulate. Yeah. Not too full. If you make it too full, then your hash table performance won't be good. Okay? Give some reasonable room. Yeah, so you can improve the performance. All right. Then you have an array. Do not sort. Yeah, if you sort, then you waste too much time, n log n. So we treat, your cost is too high. Okay, we don't want to pay that high cost. Okay, n log n. Right. All right. So given an array, yeah, n elements. All right. Yeah. So let me use this. Okay. No. Yeah. Sorry. I do not want to use arrow. So the array in the original order. Okay. Original order. All right. Then we put it in this hash table. Okay? We store array elements one by one into this hash table. Yeah. Hash table in Java is very easy. Okay? So here, to give you something concrete, here I use Java as the example. In Java, there is a interface called a map interface, right? Yeah. If you know, map interface. Yeah. But when we need to create a hash table, we need to use a class. This map is interface. You know interface in Java, okay? But when we need to create a hash table data structure, we need to use a concrete class. Implement this interface. It's called a hash map. That class is called a hash map. Okay? So we create a hash map object. So we create a hash map object. Okay? So you get that data structure already. All right? Yeah. So that hash map, each element in this hash map contains two parts. One is the key part, hash key. The second part, the value part. The data value. You have a key, then you have a data value. That's the typical structure in a hash table. You need to have a key, search key. Key used for search. Yeah. So then the data part. All right. So your elements. Okay. Yeah. All right. So the values of the elements you use as a key. Okay. Hash key. Then you need to have a hash function. Yeah. Because hash function. In Java, the hash function is built in. You don't worry about the hash function. You just put in the hash map, store in the hash map. Okay? The hash function hidden. Okay? You don't worry about that. Yeah. But we know there is a hash function do the mapping. Okay? All right. The first element by the hash key, it is mapped somewhere in the hash table. Okay? The second one, applied hash function mapped somewhere, some slot in the hash table. Okay? And so on. Each one, you apply the hash function to find a location in the hash table. Okay? Yeah. But you may have some collision problem. Two different elements may be mapped into the same slot in the hash table. That could happen. That's what we call a collision. Yeah. Yeah. Collision problem. Okay? When you get a collision, you need to map a few more times to resolve the collision. Okay? Yeah. So you can do further mapping to resolve the collision. Okay? Yeah. Yeah. Because you apply another function, to the next location and so on. Okay? But after a few times, you can find a vacant location for the element. All right. So each one, so then you use this way to go through all the elements in the array. All right. Think about how to check if the element is unique or not. When you have a collision, you compare the value. Are they the same? Because when you have a collision, the two keys may not be the same. Could be different, right? But if they are the same, you always have a collision, right? So when you have a collision, you compare. Are the two keys are the same? If the two keys are the same, you're done. You return. Okay? In that way, you only need at the most n comparisons. Because you only need to go through from beginning to end once. Okay? Without sorting, beginning to end. When you have a collision, you compare two keys. Okay? At the most, this one, at the most n comparisons. Is it a much better solution? Yeah? Much better solution. If you use hash table, you can do much better. Think about that. Think about that. Okay? Question? Hash function, no comparison. You plug in, okay? Yeah. For example, yeah, later we will talk about how to design hash functions. One is do multiplication. Yeah, multiplication probably slower than comparison. Yeah, I agree with that. When you do multiplication, modulation, division, slower than comparison. But even slower, that's a constant time times n, right? C constant times n. Some constant multiple of n, because slower, okay? But still in the category of constant times n, right? So better than log n times n, right? Think about that. Better than log n times n. Okay? Yeah, that's the point. That's the point, okay? Constant times n. Yeah. Yeah. So that's the best one. But you need a more advanced data structure. Hash table, that's more advanced data structure. Okay? Yeah. So here you can see, if you learn more, if you have more knowledge in your background, you can do better, right? Yeah. If you know hash table, you can do better. Yeah. Yeah. All right, so that's this example. All right. Definitely at this point, you may not have very good understanding because we haven't learned the hashing technique. We haven't learned that, yeah? So don't worry, yeah? So here, just to let you know, I want to make the point. Yeah. Here I use a simple interview question as an example. Yeah. Okay? Yeah. Low levels interview questions. Yeah. Yeah. If I can find time, I may show you a few high level interview questions. Yeah, relatively hard. Yeah. Yeah. This is a low level. Okay? Yeah. All right. Let's move to next topic. Yeah. Next topic, I want to say something about our project number 1. Still, there is some implementation issues I want to talk about. Yeah. So you need to get some understanding before you do your work. Yeah. All right. So today, I want to talk about the data type issue. Data type. What data type do we use in this project? Okay? Yeah. So the data type to be used in this project. Okay? Yeah. Yeah. Last time I mentioned we want to use integer operations, right? Yeah. Integer operations. Last time I said use the integer operations. Yeah, but when you use integer operations, there is a problem. There is a problem. There are several integer data types, right? Several integer data types. Yeah. Short integer, normal integer, and the long integer, right? Yeah. We want to use the largest integer data type, right? The larger the better. Okay? Yeah. So here, let's talk about the long integer data type. Long. Yeah. Yeah. Just to use this long keyword to declare integer data type. Yeah. The long integer data type in Java and C++, it uses 8 bytes. Each long integer it uses 8 bytes to represent in main memory. 8 bytes. Do you know how large is 8 bytes? How large? Each byte 8 bits, right? Yeah. A times A equals 64 bits. How large you can represent one integer using 64 bits? What is the largest number you can represent? Use 64 bits. Okay, yeah, all right. Yeah. So here, there is one question before you answer. Because this long integer has two types. One version is the signed version. Another is unsigned. Signed version, you have positive, negative case. Unsigned, greater equal to 0. So no negative part, unsigned. Yeah. For the signed case, so here, you have 64 bits. 64 bits. The highest bit is used as the sign bit. Sign bit, it means if it's 1, then it's negative. If it's 0, means it's positive. Okay? So the highest bit represents the sign of the number, positive or negative. Okay? Yeah. The highest bit is 1, means this whole number is a negative number. Okay? All right. That means the highest bit cannot be used for data representation. It is used for sign representation. So it cannot be used for data quantity representation. All right? So then can you tell me, you can only use 63 bits to represent the magnitude of the number. What's the largest you can represent? 1, 1, 1, 1, 1, right? All 63 bits are ones. What's that number? So all 63 positions, all ones, that number corresponds to 2 to the 63 minus 1. That's the largest number you can represent as a long integer. If you use the sign. Unsigned, you can do better, because unsigned, the first bit you can use to represent the number, there is no sign bit. So what you can represent? 2 to the 64 minus 1. That's the largest you can represent. Okay? All right. Yeah. So here, but for us, if you calculate this number or even that number, not too big, actually. You can see, you can use a powerful calculator, Wolfram Alpha, for example, to do the calculation. It's not too big, You can find it, certain number of digits, this long. Yeah. But our polynomial evaluation, we want to do calculation much larger than that, right? So we will get some overflow problem. Yeah. So if even we use long integer, we can easily get overflow. Yeah. That is, the 64 bits is not enough to represent our large integers. Okay? So we will have that overflow problem. What would happen when you have an overflow problem? Okay. Your computation is wrong. First, when you get an overflow, your computation is wrong. Okay? Second, there is no complaint. Okay? overflow, it happens, you get the answer, but you do not know there is overflow that happened behind the scene. Okay? You just get a wrong result. How bad it is. Well, you have an overflow. No warning. No warning. You treat it as a correct result, but actually it's wrong. Yeah. So let me tell you why the result is wrong. So when you have overflow, suppose your computation result suppose this is the correct result, okay? Correct result, because it's too large, for example, you need 100 bits to represent the correct results, okay? 100, more than 64 bits or 63 bits, okay? Then you have an overflow because large number of these high bits locations you cannot represent. You don't have them, okay? So what computer does, do truncation, okay? So this part, throw away, okay? Truncated. Truncated. It's gone, okay? Only the last 64 bits left. 64 bits left. That cannot be correct, right? After you throw away a certain number of, significant part. Yeah. So that's the higher bits. Higher bits you throw away. How can you get correct answer? You cannot. But no warning. You don't know. Yeah. You don't know. Yeah. So that's very bad, right? Yeah. So the question is, we want to avoid it. We don't want this to happen. When we do large computation, we want to avoid overflow. Avoid overflow, okay? Yeah. So here, let me talk about, because the three main programming languages used for this class, Java, Python, C++. Yeah, here, I'm talking about Java, Python, C++. Regarding the overflow problem. For Java, we need to use a special class in Java. It's called a big integer class. Use this class called big, capital B, capital integer class. Integer. This is the class name, okay? This is the class name. Use this big integer class to do the operations. Addition, multiplication, other. For our project, we only need these two. Other, we don't need. There are several other operations. You won't have any overflow, okay? No overflow anymore, all right? Even you use thousands of digits, millions of digits, don't worry, no overflow, always correct. Java big integer. Okay? Java big integer, all right, yeah. C++, there is a special header file you use, okay? A special header file. Yeah, I can give you the header name, okay? You can download, yeah, special. Yeah, you can find, if you find it on the web, special header file, okay? You need that header file. Then you can do, big operation, big integer operation, okay? Yeah. Python, if you do nothing, yeah, so that overflow happens you can do hundreds of digits, okay, before the overflow. Yeah. Yeah. So there is a, that overflow happens when the number is very large, yeah, probably more than hundreds of digits. Yeah, so yeah, at least hundreds of digits. Okay, yeah. So Python, yeah, yeah. So you can do very large integer operations, but there is an overflow. Okay, sooner or later, yeah, you will get that overflow, but very large. How to avoid? Yeah, I do not know how to completely eliminate overflow. Yeah. In Java, completely eliminate. C++ looks like can also be handled. Yeah, but Python, although that bound is very high, yeah, but if you really want to remove that bound, so then you need to do something extra. Yeah, but I do not know. Okay, I just know the overflow happens when the data is very large. Yeah. Yeah. All right. Yeah. So let's stop here. Yeah. So next time we will go to the abstract discussion, asymptotic notations. Yeah. This module, our main topic is asymptotic notations. So we will start that in our part B, next class. Yeah. All right.